So we're going to continue on here. So Newton's first law of motion says that whatever velocity an object has at a particular point in time is resistant to change. What that means is that the only way you can get an object's velocity to change is to apply what we call a net force. And I have to use the word net here because if I were to look at, I have a table downstairs in my basement right now, and there's a projector sitting on the table. And its velocity is 0. It's just sitting there. And yet there is a force of gravity acting on it, but the force of gravity is not changing that velocity of 0. What that means is that the force of gravity acting on that projector must be balanced by some other force. And we'll talk about what that other force is when the time is right. But if for some reason we have an object where all of the forces do not add up to give nothing, there's some unbalanced force, then the object will experience a change in velocity. So in order to get an object that is at rest to speed up, you have to apply an unbalanced force. In order to take an object that is moving and cause it to slow down, you have to apply an unbalanced force. In order for you to get an object that is moving with a constant velocity, which means a constant speed in a straight line, in order to get that object to change direction, you have to apply an unbalanced force. What this is sometimes referred to as is inertia. So inertia is this property, this word that we use to describe the property of an object's tendency to resist change in its velocity. And I think it's really important here. For you to talk about changes in its velocity and not something like changes in its motion. That's how you would describe it in an earlier grade. So that's why on the front cover of this handout I've got a picture of a panda bear, very, very large panda bear that's just kind of laying there. That's an example of inertia. If you wanted to get that panda bear moving, it's going to require some force. Similarly, if that panda bear, and you've probably watched videos of panda bears, they're very playful. If it saw you and got really excited and was running towards you and you just stood there, it would be like a linebacker hitting you. Just because you apply a force to the panda bear doesn't mean you're going to change its velocity much. The greater the force you can apply to it, the greater the change in the velocity will be. So in order to overcome the inertia of an object, you need to apply an unbalanced force, a net unbalanced force. And we use what are called free body diagrams in high school and university physics to explain what's going on with forces. So let's draw a free body diagram showing the forces acting on a car in each of the following situations. So a car is traveling at a constant speed on a level highway. And I'm going to put on here for a speed 100 kilometers per hour, because there's a huge misconception here about what's going on with a car moving that fast. And one of them is that the force acting on it is forward, and that's true. There is a force acting on it forward. There is also a force of gravity, and we're going to start labeling these forces. So we're not just drawing these arrows, we're labeling the forces. I don't know exactly what I'd like to call this forward force, but I guess I'll call it the force provided by the engine. And we know that the force of gravity is the force acting down. But since force results in a change in velocity, and the car is moving at a constant velocity of 100 kilometers per hour, there must be a force backwards on the car exactly equal to the force forward. This is a huge misconception. People believe that since the car is moving so fast, you must have more force forward than backward. But in fact, the force backwards, which we have to label it, I'm going to call it the force of friction. The force backward has to be exactly equal to the force forward. And there's a really simple argument for that being the case. And it's that if the force of friction backward were smaller than the forward force, the car would be speeding up. And if the force of friction backward were greater than the forward force, the car would be slowing down. That force of friction, by the way, is force of friction primarily with the air and the car, but it's also force of friction between the tires and the road. The other thing is, since there's a gravitational force acting downward, and yet the car doesn't accelerate downward, there must be an equal force upward. And this is very hard to understand, that there's some force pushing the car upwards. That force is called the normal force. And the word normal in science and math doesn't mean regular or average. Normal means perpendicular. So in mathematics, a normal line is perpendicular. That normal force is perpendicular to the surface. And the best way that I can explain why there's a normal force there is for you to imagine that I go into the classroom and I throw my big, heavy clump of keys on a desk. And then what I decide to do is do a one-armed handstand, but I do it right on top of the keys. Now, I'm not capable of doing that, but you can use your imagination. After I'm done, if you were to look at my hand, you would see an imprint on my hand of the keys. The keys would have been pushing against my hand. So not only is the force of gravity pushing me onto the keys, but it results in the keys pushing back onto my hand. So that would be the free body diagram in example 1. If we take a look at example 2, a car is speeding up. Well, if that's the case, then you're going to have a forward force provided by the engine that's greater than the force of friction between the car and its surroundings. We are still going to have a force of gravity downwards and a normal force upwards that are equal in magnitude. So we still have the normal force, and now I can start abbreviating things. We use F capital N for normal. Don't confuse that with what we're going to be calling net force later. I can abbreviate the force of gravity, of course, by just saying Fg. Usually now, rather than saying engine, what we sometimes say is applied. And there's no really good abbreviation for applied. And then, of course, we have the force of friction in the opposite direction. And if you take a look at the forces, which are vectors, I'm going to get a little bit ahead of myself, but that's okay. And I told you, please don't write this down. I told you that the applied force forward was 20,000 newtons. Newton is a unit of force. The force of friction backwards was 12,000 newtons. The force of gravity downwards was 28,000 newtons. And that would mean the normal force upwards is 28,000 newtons. And I said to you, add those forces together. Well, they're vectors. So you add them together by using rules for vector diagrams. If I were to add, and I haven't got my highlighter set up on this computer yet, I apologize. If I were to add 28,000 newtons up and 28,000 newtons down, I would get 0. So those two forces add to give 0. If I were to add 20,000 newtons to the right and 12,000 newtons to the left, what I could see from this little exercise is that the net force acting on this car, net means total, would be equal to, assuming I can subtract this morning, 8,000 newtons, and it would be to the right. And I'm doing this for a reason, even though I don't want you to write these numbers down just yet. The bottom line is there is a net force that's not balanced. There's 8,000 newtons of force on the car to the right that isn't balanced backwards. And that means, since there's a net unbalanced force, the velocity of the car is going to change. Whereas if you were to take a look at the net force acting on the car in this example, the net force would be 0. We don't need to put numbers on this. All of the forces balance, so the net or total force is 0. What about if you have a car slowing down? Well, we would have a forward force, we would have a backward force that's greater now. We also have a force of gravity downwards and the normal force up. So we have the force of friction, and of course when you're driving a car you can increase the force of friction by applying a little bit of a force to the brake pedal, which causes friction between the parts of the brake, whether they're drums or rotors or brake pads, it doesn't matter. We've got the applied force forward, and then of course the force of gravity and the normal force. And of course, the more you push on the brake pedal, the greater the force of friction is. Also, as well, as soon as you take your foot off of the gas, you're reducing the applied force forward, although there's always some compression in a vehicle engine that does want to move it forward. This is the next one that's really tough to draw because we have to draw in 3 dimensions here. So we've got a car going around a curve. The first thing we can do is draw in the gravitational force down, and that would be balanced by an equal but opposite normal force up. So we've got the normal force, we've got the force of gravity. Now you have a forward force, and this isn't going to necessarily look right, but the car is moving in this direction. And what's difficult about what I've drawn here is you need to understand that the angle between the forward force and the normal force is 90 degrees. That's a 90-degree angle. That may not look like it, but we're looking at it at an angle. So we're talking about a 90-degree angle here. Now the other thing that we must have is an equal but opposite force backward, a force of friction. So we have a forward force forward, that's an applied force. We have a backward force that's equal to the forward force. It's equal because the statement says constant speed. So if you were speeding up, the forward force would have to be greater than the force of friction. But because you're traveling around a curve, there has to be a net unbalanced force. This is tricky. There has to be a net unbalanced force because when you change direction, velocity changes. And I'm just going to go off of my script here and just say the following to you. If the net force is equal to 0, then you must have 0 acceleration, which means constant velocity. Remember, velocity is speed and direction. If you have a changing velocity, then we learned in the first unit that that's called an acceleration. And this is something that you have to think about, this statement where I said acceleration is not 0. When you see the statement acceleration is not equal to 0, what that means is there is an acceleration. It has a value. But if there is an acceleration, that means the net force must not be 0. And saying net force is not 0 is saying there is an unbalanced force. Sorry for the way this is being written. So you have 2 situations. You have a net force being 0, which means the velocity stays the same. If the net force is not 0, the velocity changes. Now, getting back to example 4, the velocity of this car is changing. It's moving at a constant speed, but since its direction is changing, the velocity is changing. And that means that there is another force here, and it's a force that's acting on the car towards the center of its radius or towards the center of its curve. And I could call this a force of friction because it is a force of friction between the tires and the road. But I would prefer to just call it the force of steering. It turns out it's actually a force of friction. It's an additional force of friction. And whatever that force to the driver's right is, that would be the net force. So again, the biggest lesson here is if there is a change in velocity, there must be a net force that's not balanced. I'm going to pause there. Does anybody have any questions about that idea? If the net force is 0, the velocity stays the same. But if the net force is not 0, the velocity changes. Any questions with that? Okay. So I'll just read through this with you. In every case, it's the net force that determines how the velocity of the car will change. The greater the net force, the greater the change in the object's velocity, which means the greater the net force, the greater the acceleration. And really, this is a very important idea that I've got here. Net force, total force, they are exactly the same thing. So if you're ever interested in finding the net force, which we will be a lot in high school physics, it means you have to add all of the existing forces together, but forces are vectors, so now comes the part of the lesson that should be pretty easy for us, because you know how to add vectors. By the way, what I'm saying here is that if the net force is 0, you get 0 acceleration. If the net force is not 0, then the size of that net force determines the amount of the acceleration. So if there's no net force, there's no acceleration. Basic. If there's a little net force, there's a little acceleration. If there's more net force, there's more acceleration. And if there's a lot of net force, then there's a lot of acceleration. This visual that you're looking at, I think, really ties together Newton's first law with what's going to be Newton's second law. Okay, so what's the net force acting on this object? Well, I feel as though I should be able to just say to you, I'm going to give you 5 minutes and I want everybody to find the net force, because you know how to do this. But given the circumstances of us being distant from each other, we're going to walk through this together. If you're adding forces that are in the same direction, you simply add them together because that's what you do with vectors. If you're adding forces that are in opposite directions, you subtract the magnitudes. And if they're perpendicular, you draw them tip to tail. So to add these forces, we're going to use a combination of those ideas. The idea that we have 85 newtons to the right and we have 48 newtons to the left, if we're trying to find the net force, which means we're going to add them, and I'll put 15 newtons up, we're going to add these, what I can immediately do is add the 85 and 48. So when I take 85 newtons to the right and 48 newtons to the left, I believe I get 37 newtons to the right. How is my subtraction, Liam? I can see you, Liam, so just give me a thumbs up. That's 37 newtons to the right. And now what you're dealing with is adding these two forces, which are vectors. 15 newtons right. Sorry. I've got my directions. No, that's right. I've got 15 newtons up and 37 to the right, so I draw them tip to tail. And again, I prefer to draw my horizontal first. It's entirely up to you, But I just prefer to draw my horizontal first. That's not very horizontal. Let me fix that. So everybody should have your calculators out. It's now a matter of using the Pythagorean theorem to determine this hypotenuse. Well, that hypotenuse, as well as the angle that the vector makes, which is up of right. I'm not really saying we're looking at a map here. I'm just saying it's up of right. So I'm not going to show my work here. We've spent a lot of time working with this. In order for me to find the hypotenuse, I will take 15 squared and add 37 squared and take the square roots. Liam, you're my eyes here. Does that look good? Okay, so we get 40 newtons. We're going to go with two significant figures. If I want to find the angle, I'm going to use tangent, specifically inverse tangent of opposite. The opposite is the 15 newtons. The adjacent is the 37 newtons. So the fact that we're adding forces doesn't change the rules of vector addition. We do the same thing we would do if we were adding displacements. So opposite divided by adjacent. And I'm obviously not in degree mode. Well, I say obviously. When you are doing trigonometry and you get an angle that doesn't make sense, it's probably because you're in the wrong mode. So it's 22 degrees. And the answer then would be 40 newtons. At an angle of 22 degrees up of right. You probably wouldn't see that, but on an exam I would just ask you to find theta. Any questions with example 1 here? All right, if not, let's take a look at example 2. If we want to add these forces together, and again, I feel as though you know how to do this, so there's not really a lot of teaching that's going on. What you are going to do is take the west and the east and add them together to get a single horizontal vector, which by my count, my total horizontal force would be 90 newtons east. And I'm just doing that in my head. I think that's right, though. $90 east? No. 340 minus 250? Oh, plus the 180. Ah, yeah. Liam, I'm glad you've got your camera going because I can at least have one person to look at, then I can see a reaction. There's actually 3 horizontals here, right? So these two, if you want to do this in chunks, give me 520 newtons east. And then we also have 250 newtons west. 270 east is what I think it is. Okay, so the total x is 270 newtons east. And the total y is, well, 125 south. And now you have to add these together. So I am going to just draw these tip to tail for you and then ask you to take a few minutes to do the calculation. Remember, I prefer to draw my horizontal first and then my vertical. That means that my hypotenuse will be south of east. So I'm going to give everybody about 2 minutes here, and I'm just looking at my computer clock. When it says 9:38, I will have the answers for you, and we will just quickly go over it. Liam, is that what you got? Okay. So my clock doesn't quite say 938, but I'm going to take 270 squared plus 125 squared and then take the square root and you get 298. And then we take inverse tangent of opposite, which is 125, divided by adjacent, which is 270. And the inverse tangent of that ratio gives me 25 degrees and it's south of east. So does anybody have any questions with that example? All right, and then the last example is the most difficult one because we are adding vectors that are not in the same direction, they are not in opposite directions, they are not perpendicular to each other. So when you have vectors at weird directions, you need to add them by taking each vector and writing an east, in this case, and north component of the first vector and writing a north and a west component of the second vector. Okay. So now what I would like everybody to do is find an east for this vector on the right and a north for the vector on the right. So we're going to have an east and a north. And then for the vector on the left, we are going to have a west and a north. I think I'm back on track now. So going back to your question, Andrea, if you wanted to leave the first vector as 35 degrees east of north and just look at the diagram, that would definitely work. So let me do my calculations now. For the vector on the right, we have 12 as the hypotenuse. We're going to multiply by cosine of 55 to get the horizontal. We have 12 as the hypotenuse. We're going to multiply by sine of 55 to get the vertical, which means my horizontal is 6.88 east. And my vertical is 9.83 north. Are we okay with those numbers? Okay. Then I'm going to look at my vector on the left. So it's going to be 15 cos 75 for my x, and it's going to be 15 sine 75 for my y, which gives me 3.88 for my x. And 14.49 for my y. Are we okay with those numbers? Okay, so, and again, I feel real bad about screwing that up. And I feel really bad because I screwed it up badly. Like I mixed up directions and angles. So now what you're going to do is focus on those four components that we found and add together those four components. If I take a look, we've got two norths, so I can add the two norths together and get a single north. The single north is going to be whatever 9.83 plus 14.49 is. Given my track record this morning, I better use a calculator for that. 9.83, well, 8298 plus the 14.48888, 7 if you like. So I'm taking my y plus my y, which gives me a total y of 24.3. Are we in agreement on the total y now? Okay, so we got 24.3 north. And then for my, so we're done with this one and this one. Now we have 3.88 west and 6.88 east. I'll take a gamble and say that when we add those together, we get 3 newtons east. These two vectors, the east and the west, are in opposite directions, so you subtract them. Now what you have to do is draw these tip to tail, which is going to give us the following diagram, 3 and 24. This is not drawn to scale, and we want to find the hypotenuse. So this is 3 newtons. This is 24.3 newtons. We need to find the hypotenuse and the angle. Shouldn't be a big problem. We have to square the 24.3 and add 3 squared. I'm not carrying all my decimals, but I really, frankly, don't care. So 24.3 squared plus 3 squared, and then I take the square root. And we get 24.5 newtons. And the angle is going to be quite steep, north of east. We have to take the inverse tan of 24.3 over 3, which gives me a whopping 83 degrees north of east. So the answer is 24.5 newtons at an angle of 83 degrees north of east. Again, sorry about that screw up. By my clock, it's about 10 o'clock, and we're only allowed to go till about 11. So I'm not going to give you a whole bunch of time here to work on these problems. What you are doing with all of these problems is you are adding forces together, but the forces you are adding are vectors. So once you read question 1, it should take you all of about 10 seconds to process that question and get an answer. Some of them get more complicated, like example 3. Very similar to problem number 4, where you have to break things into horizontal and vertical components. But what I'm going to say is that at 10:15, we are going to move forward and look at the next lesson. I am going to, while you guys get started on this, I'm not unavailable for help, but while you guys get started with this, I got to see if I can fix a couple of technical issues on my end.